Today, I want to take a look at delta-epsilon proofs and kind of how we introduce the idea of the limit within calculus and set that as our foundation for the rest of the class. Oftentimes, that foundation is a pretty rocky one. Students get frustrated with the strange algebra and the Greek symbols, and their proof skills probably aren't the best to begin with. And because it's the beginning of the year and we don't want to get off to a bad start, or what we really mean is a slow start, we kind of just push kids through it and tell them to follow the steps, fill in the parameters, and then you'll get an A on the test. I don't want to do that. I want to kind of show today conceptually what delta-epsilon proofs are, why they're important, how they go about proving that something is a limit. That way, when you get involved and start doing this stuff, it's not just following steps blindly and the math actually makes some sense, as it should, right? So what we're going to look at first is kind of this idea of a limit. And when I talk about limits, there are three words that come to my mind: convergence, closeness, and approach. And those three words I'm going to be using interchangeably for the rest of this, because limits are all about that concept. So if you look up at this graph here, we've got this nice little linear function. Ignore the side for now. Just this is a nice, happy linear function. Don't look at any of this. And if I wanted to know the value of a certain x value on the function, what I'd do is I'd take that value and plug it in. What I mean is, if I wanted to know what f of 0 was, right, I'd take 0 and I'd plug it into the function, whatever it is, or we'd look at the graph and look at 0, my function's value is 1. And that's cool, right? When we are able to plug numbers in or look at a graph and figure out what's going on. Limits answer that same question, but they answer it in a different way. So it's almost like somebody has told you, I want to know what the value is of the function at a certain number, right? Whether it's 0, -1, wherever. And here's the catch. I want you to figure it out without plugging in that specific number. So the way we can do this is by using limits, right? We can get near 0 or wherever we're interested in without actually plugging that in. We can plug in all the other numbers and kind of figure out where this thing is approaching. So what I mean by that is this. So if we look down here at this, right, here's a situation where we literally cannot plug in -1 to get our value. If this is our equation up here for our function and we plug in -1, we get 0 in the denominator, which means it will be undefined. So another way to figure that out, what the value at that point is, other than undefined, is to kind of look at the values around that. So if we look at numbers that are close to -1, like -0.9 or -1.1, or other numbers that are a little bit further off, we can kind of see where those numbers are approaching, right? As 0 goes from 0 to -0.5 to -0.75 to -0.9, as it gets closer and closer to -1, it appears that f of x is going from 1 all the way down to nothing, down to 0. Same thing if we start at -2 and move our way towards -1, right? As we start at -2, we get an output of -1, then we get -0.5, -0.25, -0.1, right? We're getting very close to 0 from both sides, and you can kind of see that from the graph. As we slide from the top down to the bottom as we approach -1 in the x direction, right? We seem to be approaching this value of 0. And as we approach from the bottom, we're also approaching that value. And that's what we define as a limit, right? Where the function is approaching as x approaches the value you're interested in, the place we're interested in. If we're interested at the spot on -1, we'll approach from both sides and see where it converges. And it converges at 0. Now, this is pretty boring, right? Because in most cases, the limit will literally be the same thing as just plugging in the number. If you can plug in the number, you should. The limit of the function at 0 is 1, the same thing as f of 0. But in other cases, f of that number, like in this case, f of -1, won't get you a value. And instead, what you'll have to do is take this limit process. It's still pretty boring with linear functions, but this will give us a basic understanding for how to do more complex ones, like this, which give us some interesting answers. So what we have here is a sine function, but with a little bit of an abomination attached to it. We have this exponential that's going to cause an exponential decay, which kind of makes it like shrink in, right? Little like a trumpet's horn. And I put the 4 and the 20 there to kind of make it bigger so it's easier to see. I also attached a line at y equals 2, f of x equals 2. That way we can see this property of this function. So while it starts out swinging kind of wildly, right, oscillating back and forth, what appears to be just shy of 6 and just shy of -2, eventually, as we go on, as we head to the right, as x approaches infinity, our function seems to converge around a certain value, and it seems to converge around 2. So we call that the limit as x approaches infinity of this function. So as x approaches infinity, the limit of this function is 2. And this is interesting because before we weren't able to plug in a number because it made an undefined answer, right? We plugged in -1 into our equation and we got 0 in the denominator. But here it's not because it's undefined, it's because you can't plug in infinity to a function because infinity isn't a number. right? But if we were able to, right, if we were to take that concept of infinity and apply it to this function in the x direction, we'd be able to see that y clearly is centering itself around 2. So it's interesting in that regard. And different functions can have different limits, and they can give you some kind of unsurprising, or some surprising but unexpected results. Results that can actually be useful. As this heads off into infinity in the x direction, we center around 2. We converge around 2 in the f of x direction. So this idea of closeness, this idea of approach, right? This idea of convergence, how do we represent that algebraically? Well, it looks like this idea is that we're getting closer and closer to a value. So we're taking a range around 2, right, which ranged from 6 to almost -2. And eventually, over time, that range shrunk down to basically infinitely small until where it was perfectly centered on 2 at all times. So in order to prove that something is a limit, we're going to prove that that range constantly shrinks down to the value we're claiming it is. So let's switch over and talk about some algebra real quick. Let's talk about ranges. All right, so let's say our limit is converging around 11. We think that it's converging around 11. We would say this. We would say that f of x is going to be around 11. Let's say within a range of, let's use some numbers. So numbers around 11, like 9 and 13. So currently our range is here. It's between 9 and 13, clearly centering on 11, it appears. And so what we can do is we can subtract 11 from both sides, and we can write this in another way. It's the exact same thing, just a different way of writing it. And now we're saying, instead of I have a range between 9 and 13, we're saying I have a range that centers on 11, and it's 2 above or 2 below. Right? Same thing as numbers between 9 and 13 is I want numbers centered on 11, 2 above or 2 below. And because 2 is plus or minus here, we can actually simplify this further. And while it looks a little weird with the absolute value symbols, it is a little more condensed. And we're actually going to be dealing with this version of this statement, right? All 3 of these statements are the same, but this version's a little bit easier to write and is actually more useful and easier to work with algebraically. So we started with values between 9 and 13. Now we have values centered at 11 plus or minus 2. And then here it's saying I want a distance of 2 around 11, right? Anything within 2 of 11. So if our particular function is a nice linear one like 2x plus 1, what values of x would I need to plug in to guarantee this? In other words, to guarantee that I always get numbers coming out between 9 and 13. Well, if I plug in 4 for x, what I get naturally is 8 plus 1, which is 9. So at the bottom, x could be 4. And at the top, the highest x could be, in order to stay within this range, would be 6, because 2 times 6 is 12, plus 1 is 13. So values between 4 and 6 for x will imply values between 9 and 13 for f of x. And just like we changed this to become this, we can rewrite this as well. This is clearly centered on the number 5. So if I do some algebra and subtract 5 from all sides, I can rewrite this such that it says, I want values around 5 plus or minus 1 from there, right? Can go up to 6, down to 4. And then I can simplify it once again with some absolute value and say I want values centered at 5, 1 above or 1 below. And this will imply that I'll have f of x values centered on 11, up or down 2, right? So what we're going to do is we're going to generalize this, that for any amount we want here, in this spot right here, right? We only want a distance of 1 in x, right? We have an interval of 1 on either side. That we will have an interval of 2 on either side here. We can shrink that down to even smaller, right? A distance of 0.5 on either side. What kind of distance will it create for our interval here? And if we can infinitely shrink this down, and that it still implies this, that we're still centered on 11, but our range is shrunk down too, that means we must be centered on 11, and 11 must be where our function is converging, where our limit is. So these values here, since we're going to generalize them, are going to need some variables. And in calculus, we use these Greek symbols. Delta for our domain shrinkage, right? We're shrinking in the horizontal direction, right? That's going to be the distance around our interesting point, 5. And then epsilon is going to be the vertical version of that, right? We're centered around 11 and the distance either up or down from it is epsilon. And as we shrink this, will that mean that this will shrink too? That it will still stay centered on 5 as we shrink it down, and it'll still stay centered on 11 as we shrink that down, right? As they connect. So let's talk about these connections. So if we look at our function, 2x plus 1, here's an interesting value, whatever value we're interested at. We're trying to find the limit at this point. So if we look, delta is our range around here, right? And that naturally corresponds with a range here around L. I think I'm missing an L here. And so as that range contracts and gets smaller and smaller, really what it's doing is the relationship between how much we contract this and how much this gets contracted as this shrinks will be equal to the slope, right? Because that's really all this is. We're having a horizontal change over a vertical change. And so for a linear function, the slope will be the relationship between epsilon and delta. And that relationship is something we're going to have defined to do our proof. So we've talked about the algebra and what that looks like. And we've also talked about how we need to find the relationship between when we make a change here, how much does it change there, right? And for linear functions, it'll end up being the slope. Things will get more interesting once we get curvy functions, because a small change in here looks like it's going to produce a similar change here. But of course, if I look at a different part of the function, right, if I wanted to find the limit here, that change will be different, right? A small change or even a large change in the x direction over here doesn't produce much at all of a change vertically, right? It pretty much stays flat. So the slope or the change that we're having here is different in different spots on a curved function. Whereas on a linear function, the change is always going to be the same. Doesn't matter where you look. Even if I look down here at a range down here, it'll still be the same relationship between epsilon and delta. So start thinking about this. We'll get into that later. We're going to start with the basic foundation for linear functions and then apply this to curvy functions. But that relationship between delta and epsilon will depend on the location that you're looking at, right? In this range right here, it seems that they have a similar relationship on either side. But this range right here, it looks like no matter how much you change delta, epsilon doesn't change very much at all. So different relationships for different locations. So how do we do this proof? Well, again, what we want to prove is that if we have a small, infinitesimally small domain around a point we're interested in, we'll call that C. And the size of that domain will be delta, right? The difference between x and C. And of course, we want it to be an actual distance. So can't be 0, right? We do want some space around it. We want to show that no matter how small we get here in the x direction, that will always imply a similar change in the f of x direction. Centered at C in the x direction and centered at L in the f of x direction. And if this is true, if we can shrink down infinitely here centered on this point, and this will also shrink down infinitely centered on L, then what we know is that L must be our limit. It's where our function converges. So if you remember back from algebraic proofs, two things. One, if we can take an algebraic statement and manipulate it algebraically to look like the other, then we know that we have causality, right? We have that directional arrow. The other thing is that it's always easier to start from complex and simplify rather than to go from simple to complex. So what we're going to do to get started is some preliminary work is we're actually going to start here and work the arrow backwards to figure out what the connection is. That way, when we do go this way, we have a bridge to get there. And you'll see what I mean when we do that. So let's start with an example. Let's use the same example as before. Let's say our function is 2x plus 1, and we want to know the limit of this function as x approaches, let's do 5 like we did previously. So as we center around 5 in the x direction, as we converge around 5, where does f of x converge around? Well, we're going to predict that it's 11. That's what we want to prove. So to do that, we're actually going to start out over here. F of x is 2x plus 1, and L is 11. There we go. And that's going to be some range, right, between our function and the value we're interested in, right? And so what we're going to do is we're going to take that and make it look like this, right? Same thing, except the 5 is in place of the C. So what I'm going to do is I'm actually going to simplify this middle. And what I get is 2x plus 1 minus 11 is minus 10. And we need to get to x minus 5 in the middle. Well, luckily, I can pull out a 2 from here, right? 2 is positive, so pulling it out of the absolute value doesn't change anything. And when I divide everything by 2, what I get is this. 0 divided by 2, of course, is still 0. Epsilon divided by 2 is epsilon over 2. So this is the same thing as that, working backwards, if and only if delta is the same thing as epsilon over 2. So we're going to use that fact that the relationship between delta and epsilon is that delta will always be half of epsilon, meaning that if our distance on either side of 5 is 2, right, that means the distance on either side of 11 must be 4, twice as much that, or vice versa, right, if you're looking at it this way. So now that we did the preliminary work to figure out this, our relationship between delta and epsilon for this particular function, we're going to use that to prove that this implies that. So we're going to start here. We have some distance between our range and where we're centered around, and we're centered around 5 horizontally. That distance is delta. And we're going to prove that for any delta, it will imply any epsilon, any shrink there. So we're going to use this fact, and we're going to say let delta be related to epsilon in this way, that it is always half of epsilon. And if that's true, we can start out very quickly with a quick substitution. Grab some orange. So centered at 5, our range is this. It'll be half of whatever the center is around 11. And what we're going to do is we're going to manipulate that to look just like this. And this is just going to be these steps in reverse, essentially. So what we're going to do is we're going to multiply both sides by 2. And because 2 is positive, I can put it inside the absolute value. Now I've got less than epsilon. And we're really close. The next thing we need to do is make that minus 10, change that minus 10 into a plus 1 minus 11, which of course is the same thing as minus 10, so we could do that. I'm going to box this so it's clear that my original function is 2x plus 1. And if we subtract 11 from that, right, that's still the same thing as minus 10. So didn't change the problem, just made it look differently. And now we've done it. We've shown that this automatically implies this when delta is epsilon over 2, using this key factor right here. So what this means is that as we're centered on 5, we have a certain range, and that certain range will automatically lead us to be centered on 11, our limit, with a certain range. So we would say, therefore, the limit of our function as x approaches 5 will equal 11. And there's our proof. And then we'll talk about more complex functions next time that are nonlinear.